So today we got another Neil deGrasse Tyson video. Neil deGrasse Tyson, why science doesn't make laws anymore.
Till the 20th century. Everything that physics discovered about the universe that applied everywhere, as far as we knew,
Right.
they were called laws. Newton's laws of motion.
Right.
Newton's laws of gravity.
Right.
Law is something that you don't break.
Okay.
It is a law.
That's right.
Thou shalt not go faster than light.
There you
Thou
go.
shalt not.
Those were the original tablets, if you're wondering.
No, that's the other one that broke.
That's the one that broke off. I come down with these 15. 10
11 to 15 with the speed of light.
Right.
Okay, so is it because, let's try before they jump into it, let's try to guess. Is it because that there's nothing more concrete to be discovered yet? Like everything is so abstract now that, we can't quite define it as concretely as a law? Have we discovered all the fundamental laws, or is it something else? I'm not quite sure.
So, beginning of the 20th century, we stopped calling them laws.
Okay. Why is that?
It was a humble recognition that the experiments you do that establish the laws might not have been conducted in every possible extreme to test the law that you're establishing.
That makes sense.
Okay?
Right.
So it's kind of like realizing that, yes, for the experiments that you're doing, these definitions and laws that you've set, they are laws within the constructs of your experiments that you're doing. But outside of that, there could be some edge cases where not everything adds up the way you'd expect it to. And some of the laws that you set can actually be broken, which doesn't actually make them laws. So they're a little bit more reluctant now to call them laws because they admit that they don't know every possible scenario for these laws that they're setting.
Let me give a really stupid example.
All right.
I can make a law that if I drop something, it'll fall at a particular rate. I'll call that my gravity law.
Well, it kind of is the case.
Yeah, it is. However, if I go to a mountaintop, it'll fall slightly slower if I have very careful measurements. My gravity law is different at the top of a mountain. So I have to adjust it somehow. And then I learned, oh my gosh, my gravity law depends on how far away you are from the
I didn't know
center of
that
the
was
Earth.
true. That
Okay.
well, I guess, yeah.
Because that's what it's falling into.
Oh, that's what it's falling into. But you have to, this is new understanding of what's going on.
Right.
But if no one ever ascended a mountain, this law would work for everybody at all times at sea level.
Right.
Okay?
Yeah.
But so now let me give a more realistic example. Isaac Newton has his laws of motion, laws of gravity. They apply everywhere. The moon going around Earth, Earth going around the sun, Jupiter's satellites going around Jupiter. It's not just, here's what the sun does with planets. It's what anything does. That's
Right.
got, okay.
If it has mass, right?
If it's got mass, you're going to have gravity,
Right.
you got this.
Right.
So, oh my gosh, this is amazing. But then Uranus.
Imagine if
discovered.
gravity only existed
It's
on
not
Earth.
following Newton's laws of gravity. Have we found the limits of this law? It only applies maybe to our solar system, maybe other star systems, it's different, or maybe beyond a certain distance, the universe is somehow interfering with it. We didn't know.
Right.
And we had Newton's boys on his side saying, Newton is so badass, we are sure the law still works. There must be some other planet tugging on it that you haven't put into your equations.
Right.
Let's look for it. You have to invert the equation to find the thing that would be making the force of gravity.
Right.
It's called an inversion problem. Took some high-level math in the day. Sure enough, they said, look here, bada bing, there it is. Newton's law still held.
Still help.
Now, we keep going. How about these stars that orbit each other? Do we know their masses? Not quite yet. We have to learn more about what stars are. We get their masses. Whoa! They're following Newton's laws.
Wow. Right.
Stars, that's beyond our solar system.
So Newton's laws keep holding up, or at least they did for large bodies in the solar system. But obviously we know now quantum particles don't have the same result that you would expect from just gravitational forces. There's a bunch of other forces on the quantum level that dictate how quantum particles move. So you can't just use gravity at every scale to measure everything.
We were good with Newton's laws until we had to understand what Mercury was doing. Mercury
Ooh.
its orbit around the sun was not following Newton's laws. We said, we've been down that road before.
Right.
But there's a planet.
Right. Inside the sun.
No.
I didn't know this.
There's a planet in the sun.
No.
Pull it on Mercury.
The next best thing. There's a planet so close to the sun,
Right.
we can't see it. It's lost in the glare.
Okay.
But clearly it's there.
Clearly it's there.
Oh.
Okay, because that would account for the fact that Mercury's path is not exactly...
Wait, so they made up a whole planet called Vulcan? Imagine if that planet actually existed. I still think we should. I think we should incorporate more planets into our solar system, just to shake things up a bit. Even if they're not following the rules of planet, I think we should bring back Pluto, a random asteroid, call it a planet. I just think in order to grow as a society, we just need more planets. We need more planets. I'm sick of just the 8 that we have right now. Can we get some more, please?
Following Newton's laws.
Right.
Turns out, can't explain it with Newton's laws. We're in the presence of severe force of gravity. The sun. Obviously, Earth is near the sun. We're orbiting it. But these effects don't show up until you're really close. And Mercury is really close to the sun. And a whole other understanding of physics needed to be invoked. Einstein's general theory of relativity.
Enter Einstein, which accounts for very high sources of gravity, very high speed.
So, yeah, I wasn't understanding why you couldn't just use Newton laws for Mercury. So because the sun is so massive, it's warping time space? Is that accurate? It's warping time space so that you can't just measure things using gravity because time and space itself is being warped and changed, and there's other effects at play here just because the gravity is so high. And I guess those effects are always going on, but you can't really measure them until you have something so incredibly massive or so incredibly fast, the sun, or something going really close to the speed of light or something like that.
So you invoke Einstein, Mercury is bang on. Exactly
No
as it
more
should be
Vulcan.
behaving. Do we throw out Newton?
Yes.
No. Newton.
Get out, Newton, you dumbass. Get out of here.
Newton got us to that doorstep.
Right. Took us as far as we could go.
And according to Newton's laws of motion, if I'm going 2/3 the speed of light and you're going 2/3 the speed of light and we pass each other, how fast are we going relative to each other?
Half the speed of light? Right.
No. One. In Newtonian way, it would be 1 1/3. So 2/3
right.
plus
We're
2/3.
adding them.
You add them.
Because I'm going fast, you're going fast, but we're passing.
Yeah, a simpler way to do it is I'm going the speed of light, you're going the speed of light. You're passing me twice the speed of light.
Twice.
Okay?
Right. That's it.
No, it doesn't work that way.
No.
Okay?
Right.
Because
That's something that's so weird to me. That's something that's so weird that, like, obviously, if you're going 60 miles an hour and somebody's going 60 miles an hour towards you, then like your relative speed is like 120 miles an hour compared to them. Like you're going 120 miles per hour at them. Like imagine them stationary. It would be like you going 120 miles per hour towards them. But when you approach the speed of light, that no longer applies for some reason. Let's find out why.
the speed of
You
light,
can't do it.
the
Right.
speed of light sets a limit unknown to Newton. Unknown.
Right.
That there should be any such limit at all, because he never dealt with anything going faster than running horses or just planets in orbit around their stars.
Okay.
They're not going fast enough to manifest that failure of Newton's laws. Okay. You take
Interesting.
Einstein's...
I love the way you put that.
But okay, he explained why. Obviously there's a limit, but he didn't explain what happens when you have two objects going towards each other near the speed of light. Okay, I looked it up. I couldn't find an answer that was satisfying enough, so we'll have to see another video about that. Well, right now, let's just assume we understand.
No, it's like people who work out and they say, work out to fail. Like, in other words, you push the weight as far as you can until you just can't lift it anymore.
Right.
And that's the point of failure. You can lift that. You could, but you get to a point where, this doesn't work anymore.
You've tested the limits of your muscle.
limits of your muscle.
There
So
it is.
now you're in a new world now.
Are you going to get there or you're not? Maybe you need a different regimen.
Right.
To get there.
Exactly.
Okay.
That's very cool.
Einstein's general theory of relativity and special theory of relativity combined accommodated the extremes where Newton's laws had never explored. This was a humble recognition that which we used to call a law had limits.
Yes.
You can't call things laws going forward.
Right.
Because the next thing might also have limits.
Right.
So let's be humble.
I think that's awesome. Like the humility to do that. Yeah, I feel like science back in the day, to a certain extent, it's still like that. But back in the day, they were so certain. And then like new scientific findings, it's not even just science. With like the Catholic Church not accepting that the earth rotated around the sun, that the sun was at the center of the solar system. Just people's understanding of the worlds were so set in stone and concrete. It was so much harder to change people's minds about how the world works. And today it's still hard, but I think it's cooler that we're more flexible with our understanding of how the world works and more willing to accept that we're wrong. I think that's a great trait as a society to have.
About this. And so Einstein's theories of relativity are called his theory of relativity. So out of a point of historical perspective, we still call them Newton's laws.
Okay.
Just that's an historical artifact.
Like an homage.
An homage,
Yeah.
yes. But entering the 20th century, where these
Newton's
laws
theories
of 19th century classical physics fell at their limits, we said we're not going to make that mistake again. Okay, so here's what's important. If you take Einstein's relativity, plug in low speeds and low gravity, they become Newton's laws. So Einstein's laws did not replace Newton. They extend.
I guess that's kind of what I meant earlier, that like those things are always there, even if you don't have something super massive. It's just you can't really detect it. Yeah, you can't really detect the effect of like my gravity on this camera's gravity too much, because you know there's so many other stronger forces, and like you can't detect my gravity's changing of time space's effect on time space because it's just so small compared to like something like the Earth or the sun.
Ended them.
That's pretty wild.
That's how science works. Newton's laws don't all of a sudden not work.
They're not supplanted or erased.
In the realm in which they had been experimentally tested and verified.
Right.
That's still true.
So they still work.
The Apollo program, we went to the moon on Newton's laws. There was no Einstein in any of those equations.
Right.
Come the 1920s, we are recording this in 2026. We're in the centennial decade of the discovery of quantum physics. In the day, we called it quantum mechanics. That extends classical mechanics into the realm of particles and nuclei and the like.
Okay.
Still call it quantum theory, even though every experiment ever suggested by it has verified its predictions.
Oh, okay.
It is as much a law as we have ever measured anything to be.
It's
Yet
just
we
that
still call it quantum theory.
Because at some point, there's a failure. We haven't gotten
there yet.
But we know at some point.
We don't know.
Well, we don't know.
We
can allow for it.
Allow for that possibility. People think a theory scientifically is just some idea you happen to have that's not yet verified.
Yes.
Like definitely growing up, I was confused about this too. Theory sounds like a hypothesis. It sounds like a hypothesis, and like some people treat it the same as if it's a hypothesis, but in reality, it's like it's been super tested. In order for somebody to release something like a theory, they have to have done a rigorous amount of testing and things like that. And of course, like theories can be wrong and things like that. There's different levels of theories and to what extent they've been tested, but it's not just something they came up with on a whim. Like the theory of evolution, I think is more so by a lot of people is treated as if it's just a thought experiment, and it's just like like yeah, we see these fossils and you know it kind of looks like this one, so we think that humans evolved from apes, like, but in reality it's so much rigorous studying of fossils and like the links between them. It's just a lot more concrete than a lot of people give it credit for.
Nothing could be farther from the truth.
Yeah.
In physics.
Because they think it's a murder mystery. Just like, I have a theory.
Okay, so when people say, I have a theory,
Right.
you know what my reply is?
What?
I say, Einstein had a theory, you have a hypothesis.
Right. And guess what? You don't even have that because that's an educated guess. Okay. You know what you got? You got an idea, a thought.
You have a thought.
That's what you have, a thought.
So the difference is a theory, as we now use the term and have been using it for 100 years now,
Okay.
is an organizing understanding of how the universe works in some realm or another. It not only organizes it, it says we understand this, that, and the other because of this idea. And not only that, this idea is so fertile, I can make predictions on it. You can go test it, and those predictions will show up and be correct.
That makes sense. And especially because it eliminates the perception that a theory is a thought or an idea. Like, oh.
That's why whenever I get the occasion, I say, you don't have a theory. Einstein had a theory. You have an hypothesis.
Right.
You hypothesize something.
Right.
It's not, nothing works yet.
Right.
It hasn't been tested yet.
Right.
Okay?
Right.
I have a hypothesis. Can we test it? Yeah, here's an idea. Test it. We test it. Did it? Yeah, okay, that's good. Hold on to that.
Right.
Is there more testing? Is there more understanding that this will give us? As this builds, you achieve the level of a theory.
Gotcha. Yeah. Okay.
So we have quantum field theory, theory of relativity. We have the theory of evolution.
There we go.
Nothing makes sense in biology without evolution by natural selection.
And by natural selection, we mean God decided to, like, I'm going to select you, and I'm going to select you, and I'm going to select you. And
That's divine selection.
That's divine selection? Okay.
So evolutionary theory, for example, would say, if you understand that mammals came later in the tree of life, we didn't really become interesting mammals till after the dinosaurs, the big dinosaurs left the scene. I think there were some early mammals. But if you go back millions of years before the dinosaurs, and there's a sedimentary layer with dinosaur fossils, evolutionary theory predicts you will not find...
Guys, there's some people who don't even believe that dinosaurs existed, and that hurts my soul. That hurts my soul. That's one of my pet peeves. I haven't encountered too many people like that, but I've definitely encountered some, and oh my god, I gotta tell you that's soul crushing to me, because it's like their idea of reality is so warped. Not all of them are like stupid people, like some of them educated to some degree, but obviously not enough, and obviously not in the right discipline. You can obviously be really good at math or something like that, but not have a good understanding of biology. It doesn't necessarily always translate, unfortunately. Hopefully, if you're out there and you don't believe in dinosaurs, please, I'm begging you. Just I don't even know how to say that, because like that's such a gap, and that's such a distrust in so many aspects of society that it's just like, I feel like you might be too far gone.
Mammals in that layer. If you find a layer that has dinosaurs and rabbits, that's a problem for the theory of evolution.
It's also a hoax.
So you have to ask, is it a hoax?
Right.
Because evolution has been so thoroughly tested.
Right.
Is it a hoax? Is there some uplifting of the surface, which happens in continental drift? So check for that.
Right.
You want it because it's been so successful. Your first thought is, no, let me throw the whole thing out the window because of this one data point. Because it's been so successful. That would put a theory to the test.
Right.
Now, Copernicus had a theory. It's the heliocentric theory, that the sun is in the middle of the known universe, not the Earth. He came up with this. It was like, whoa, brilliant Copernicus. He's right. Sun is in the middle of things.
Right.
But his orbits were perfect circles. He's religious like everybody else. Oh. If God made the universe, what's the most perfect shape? Circle. So he made the universe, give the boy circles. And it didn't match the paths of the planets in the sky.
Oh no.
How could this be a correct theory if it's getting that wrong? So here's what happens.
The Lord works in mysterious ways.
That's one answer. Another one is, maybe I have to adjust my theory. Maybe the basics are correct, but I got to make an adjustment on the edges. What is that adjustment?
I think that almost takes more intelligence to not throw out an entire theory in itself and like the concept of adjusting it. Because I think a lot of people are like, oh, this doesn't work. It doesn't work. I failed. They would just throw it out. But to have the sense to like say, okay, I think some of this is right. I got to figure out what's wrong. I think if I adjust these aspects, then maybe I will get the correct measurements this time. I think that takes so much more intelligence.
Learned 70 years later, they're not perfect circles. They're slightly squashed circles, ellipses. Once you put in ellipses, it's bang on. Just because you find something that tickles the edge of a theory,
right,
that alone does not mean you're going to throw the theory out if the theory has a lot of supportive experimental evidence.
Does every planet in a solar system, like not like outside of our solar system, does everyone follow an ellipse, or are they more generally circles in certain instances? Is it just a natural impact of orbit that it's an ellipse, or is that just because of like the gravity in our solar system from the planets just so happens to be that way?
Take the Big Bang. I cannot begin to list for you the supportive evidence for the Big Bang, even though it makes no sense that the whole universe was once smaller than a marble. What's my saying?
The universe is under no obligation to make sense to you.
Thank you.
Right.
Thank you.
And I have a response to that. F you, universe.
You're going to make sense to me whether you like it or not.
That's right. I want to make you make sense.
Don't make me make you make sense to me. So right now, there are measurements of the Hubble constant that don't agree with each other.
Okay.
The Hubble constant is like the expansion rate of the universe. What's up with that?
Right.
Headlines all over the place. We have to revisit the Big Bang. The Big Bang this.
Big Bang doesn't work anymore.
Okay, excuse me. No, this is like an edge effect. If we have to redo the Big Bang, it's going to take more than that.
I don't think you should ever be like super eager, excited to disprove something without actually doing research yourself. Like I think that's what happens a lot with like religion and certain aspects of science that doesn't align with religious texts. It's like if one thing is incorrect or we have to reevaluate one thing, then they're like, we got him. Science is bullshit. But in reality, like they would never do that to a religious text themselves. They would look at science with so much scrutiny, but you would never do that to your own religious text. And it's not that like religion is just patently wrong or anything like that. It's just like you should keep that same energy. You should quite literally just keep that same energy and practice of scrutiny with your own religious text if you're going to do that with science. Like it's okay to be skeptical, but don't pick and choose what you're skeptical of. Just don't pick and choose.
This is one thing. Let's keep exploring it because so much else works. If you have another idea that can explain the Hubble constant, you have to explain all this other stuff too.
Right.
And that's hard. Be my guest. But just don't turn around and say, I found this one thing that conflicts, therefore
all of it's wrong.
All of it's wrong.
That's called the baby with the bathwater.
Exactly. In Copernicus, the baby was right there. The sun was in the middle. You're not throwing that out.
Right.
Because it explains so many other things.
Yeah.
Okay?
Yeah.
All right. So, theories are powerful ideas that have been experimentally verified, and we ought to be calling them laws, but we don't because we're humble. And we're going to say one day we might find a deeper idea in which this theory is embedded that gives us a deeper understanding of how the universe works.
Right.
But whatever that new theory is that supplants it, it doesn't push it to the side because it's experimentally verified. It will enclose it as a special case of the deeper understanding of nature.
Nice.
To say, and this was spoken in the halls of Congress, we should teach evolution as the theory that it is and make sure that we can also teach biblical creation because evolution is just a theory. That is a profound misunderstanding of what theories are and how and why they work. As our understanding grows deeper, so does the...
These are our politicians. It's crazy that like you can dedicate your entire life to becoming a politician and still not be that smart.
Nesting doll of the prior understandings and how they manifest in the world that we...
Politics is basically just the study of controlling people, really. That's what I feel like it's become. Because I never felt that a politician is genuinely... I rarely feel that politicians are genuinely interested in the interests of people, like the best interests of people, rather than their own political career. And fair enough. I mean, like with any other profession, for the most part, you're interested in your career, but that's just a very dangerous profession to have and be interested in your own career, because you're playing with people, you're manipulating people, you're just pulling for people's votes so that they can push you up in hopes of you reaching down and giving back to them. Like, I think it's such a weird profession.
The explorer.
Pretty cool, man. I
There
love
you
it.
go. That's it, Chuck.
That's it.
We good on that?
Yeah, we are.
All right. Well, that was super interesting. I love these Neil deGrasse Tyson videos. Like the way he explains stuff. I think we're gonna look back and just he's just gonna be a treasure of science communication.